Gravity is everywhere, then why doesn't it all just cancel out and the universe just be a sea of hydrogen, helium and neutrinos? Hi, I'm Seti, a PhD student in astrophysics, and today we are covering Seeliger's paradox. This is part 5 of my mini-series on astronomical paradoxes. Last time we covered the black hole information paradox, but check back in 2 days' time for part 6. As a little bit of context, Hugo Seeliger published this as proof against Newtonian mechanics back in 1895, so this would have been before GR, or general relativity, and quantum field theory were very well established, but this would have mostly been concerning Newtonian mechanics, with a couple additions from Gauss and Poisson. Seeliger states in his paradox that if the universe were infinite and static, then all of these stars should be roughly evenly distributed, which is where all of the gravity comes from. They didn't have supermassive black holes and like supervoids and superclusters at the time. In fact, I don't even think they had the concept of galaxies. So all the stars are evenly distributed, all of the gravity is within the stars, but they all have their own mutual pull to each other. And if the universe is infinite, then there should really be an infinite pull in all directions, cancelling out all of the gravitational potential and therefore the force. Seeliger here is using what's called the shell theorem, which in a nutshell, no pun intended, states two important things. One, that you can estimate the gravitational attraction as coming from the centre of the object, so you don't really need to take radius into account. And two, if you are within a hollow shell, so all of the gravity, all of the mass is only on the surface of that shell and there's nothing inside, just you, the potential acting on you is a net zero. It all cancels out and the resulting force is also zero. However, if you are in Seeliger's specific scenario where you have an infinite amount of shells, then if you move your point so that your coordinate system and your point are no longer aligned, you just shift it a little bit, you can get a non-zero force. This is because then you're able to trace out a shell where centered around this new point, this new origin of the coordinate system, but that you're on the surface of it. So you do have a net resulting force, which is proportional to g/m over r squared. Everything beyond that point, you can just use the infinite shell theorem that Seeliger made up again. Well, not made up, but Seeliger used, and the rest of that all cancels out. Seeliger saw this variable force depending on your coordinate system as a really big flaw, and he was correct to point that out, but he just then assumed that Newton's laws were completely wrong. He proposed that there were either two incorrect things going on here, either that the universe was not infinite and it wasn't static, or that Newton's laws were wrong, and of course he chose the latter. The problem is actually, since the universe isn't finite, especially concerning the stars, you can't apply the shell theorem to infinity here. It's not actually a realistic setup of the gravitational potential in the real universe. Also, he's kind of misestimated the potential in a way. Because it's meant to be a continuous quantity, he's then chopped it up into discrete bits and then sum them up into a conditionally convergent series. This has kind of made him set up to fail in a way, but of course Seeliger wouldn't have known that at the time. You can actually fudge many laws to get the same result, like the electrostatic propulsion, any of Gauss's laws, you can kind of do the same thing. So this isn't unique to Newtonian mechanics, it's kind of just a flaw in the setup that Seeliger has used. Instead, a much more robust way is just to either solve the Poisson equation, if you can even do that. That's not an easy task. Or you can just integrate Newton's law of Newton's formula for potential up to infinity, which actually offers a much more robust way of estimating potential. But that wraps everything up for Seeliger's paradox. It definitely did not hold much weight even during its time, its heyday, but it is really interesting to read and learn about nonetheless. Thank you very much for joining me. I will see you in 2 days' time for part 6.